And now we come towards some applications of the Stokes law. So Stokes law is given in terms of the force, that is the viscous force. Now the very first application is that velocity of the raindrops is very small in comparison to the velocity of that body falling freely from the height of cloud. So if raindrops are falling, then the velocity will be small. But if some another body, that is heavy body, is falling freely from that height, so we will find velocity of the raindrop will be small, whereas the velocity of the body falling freely from the height of clouds will be more. Another point is descending by parachute with lesser velocity, etc. Now, descending by parachute means, so obviously a person is flying in the airplane and the person is descending with the lesser velocity if the person is using a parachute. Now, next come important points about the viscosity. Viscosity, as I have told earlier also, again and again, it is a kind of friction between the layers, various layers of the liquid. That is what the meaning of viscosity. And viscosity is affected by temperature. So, using the viscosity of liquids or air, damping is produced in some instruments. When we use the term damping, it means damping is normally a term related to a wave in which the amplitude continuously goes on decreasing. So when we use this term in the viscosity of liquids, it means we are referring to the energy loss. That is, damping is produced in some instruments, means there is some energy loss when we use certain instruments for understanding the viscosity. If two vessels of similar size contain water and mercury, so what we have done, we have taken two containers of the similar size, one is containing water and other is containing mercury. And the liquids are filled right up to the same height and there is a small hole in the wall of the vessel at the same depth. The velocity of the water and mercury emerging out of the holes will be same. So when the liquid is there, one is water and other is mercury, from the hole the liquids will come out but their velocity will remain the same. The range of the streams of both liquids will also be same. Range of the streams will be the same because the velocity and the range of liquids do not depend upon the density. So density only affects the viscous force. On blowing the air in between the two balls suspended close to each other, the balls are attracted towards each other because on blowing the air, the velocity of air in between increases, hence pressure decreases. The next concept is a vessel is filled with liquid and there is a hole in it, that is hole in the vessel. So, hole in it through which liquid comes out. Liquid is oozing out. If the size of the hole is increased, the velocity of the liquid emerging out will remain the same. But the volume of the liquid emerging per second will increase. So, in a nutshell, we can say that if we consider a vessel filled with liquid and if we make a small hole or a big hole, we will find that velocity of the liquid coming out of the hole won't change, but we find that the volume of the liquid emerging out will be different. So emerging per second will be increasing. Now we are referring to what is an ideal liquid. Following properties are found in an ideal liquid. When we use this term ideal, practically this is not achievable. Ideal, 100% work cannot be achieved or 100% performance cannot be achieved. It can be very close to 100%. So what is an ideal liquid? In an ideal liquid, we find zero compressibility. Zero compressibility means it cannot be compressed, but liquids can be compressed. So an ideal liquid is incompressible, we cannot compress it, That is, on pressing the liquid, there is no change in its volume. That is what the meaning of zero compressibility. Practically, this is not true, but theoretically, we'll say this is an ideal liquid. So, in most of the numerical problems, our assumption will be that the liquid is ideal. However, practically not true. Now, another thing is there are certain short examples on the basis of Stokes' law or the compressibility or the viscosity. Like our first question is, there is 1 mm thick layer of glycerine between a big plate. So we consider the plate and we put some glycerine 1 mm thick. So between the layers there is some friction. So that is called viscosity. So there is 1 mm thick layer of glycerine between a big plate and a flat plate of area 100 centimeters square. If the coefficient of viscosity, that is neta, of the glycerine is 1 in MKS units, the force required to move the plate with velocity of 7 centimeters per second should be how much? So to solve this question, we take that is the viscous force. The viscous force is given by formula neta A dV over dz. So for neta we put the value of coefficient of viscosity, then area we will put, if it is in millimeters square, we should convert it to meters square, and dV by dz is 7 into 10 to the power minus 2 over 10 to the power minus 3. So our solution will be that the force to overcome viscous force is nearly 0.7 newtons. Now we proceed with the second question. The height of the water in tank is h. So there is a tank and water is filled in that tank. The height of the water in tank is h. The range of the liquid emerging out from the hole in the wall of the tank at a depth of about 3 by 4 times of h, that is 75% of h, from upper surface of water will be how much? So the 4 options are given. That is, number 1 is h, other is h by 2, the third one is 3h by 2, the fourth one is root 3 over 2 times h. So we proceed with the following solution. That is, first of all, we use the formula for the range of liquid, which we have done in the Torricelli equation. So according to that equation, range of the liquid is given by x, and it is 2 under root h into h minus h, where h is given according to the question 3 over 4 times of the height of the liquid column and the tank. Now we put the values. So x is equal to, we have written already the formula, that is 2 under root h into h minus h. So for h we will compute the value. The remaining numbers are as it is. The whole equation will be in terms of h. So x will be calculated, and after all calculations we find it will become root 3 over 2h. So this is the right answer, and that is the fourth option. Now we come towards the next question, that is 2 horizontal pipes. So we take 2 pipes, they are horizontally placed, their radii are 1 centimeter and 2 centimeter, they are connected with one another. So radii, one tube is narrow, slightly is wide, and water is flowing through them. If the velocity of water in the first pipe is 8 meters per second and pressure is of the order of 10 to the power 5 newtons per meter square, then the pressure we have to calculate in newtons per meter square, and the velocity in meters per second of the water will be how much? So again, the 4 options are given. We have to select the right option. To proceed for calculation, we proceed as follows. Now we are going to use the principle of continuity, that is A1 V1 equal to A2 V2, and from this we get the value of A1 over A2, which is found to be V2 over V1. Now area of cross section of the one tube is pi r1 square, and area of cross section of the another tube will be pi r2 square. Pi will cancel off and we will get V2 over V1 as R1 square over R2 square, or V2 over V1 will be R1 over R2 the whole square. Now we will compute the value of the radii and we will get the values of V2 over V1. So V2 is calculated by composition V1 into R1 over R2 the whole square. And now by putting this value, we will get like this. That is 8 into 1 by 2 square. That will become 1 by 4. So it is 8 over 4 and 8 over 4 will be 2. Now we use the Bernoulli theorem. That is P2 is the pressure. P1 is also the pressure plus half rho into V1 square minus V2 square. That is the velocities in the two tubes. And when we use this from rho, that is the velocity of the body in the liquid or the viscous liquid. So now for P1, we will compute the value because it is being given to us. Then we write half. Rho stands for density. The density of water is 1000 kilogram per meter cube. And then we write V1 square minus V2 square. So both values are written. And after all calculations, we come to the conclusion that the pressure P2 will be equal to 1.3 into 10 to the power 5 newtons per meter square. Now we come towards another question, that is the water drop whose radius is 0.0015 mm. So first of all, we must convert this value into meters. So it is millimeters. We divide by that is 100. We get it centimeters. Then we divide it by that is 100. It will come to meter. So millimeter to centimeter, then centimeter to meter. Now this water drop is falling through the air. If the coefficient of viscosity of air, now you will remember that air is basically a fluid, so it will obey all the laws of the fluid mechanics. So the viscosity of air is 1.8 into 10 to the power minus 5 kilograms per meter second. Then assuming the buoyancy force as negligible, whenever some body will float in water or is dipped in water, upthrust comes into action, that is the buoyancy force. So we are assuming that the buoyancy force is negligible. The terminal velocity of the drop will be how much? That is, we have to calculate the value of V. Now, 4 options are given and we have to select the right option. So which formula we are going to use? The formula will be 2 over 9 R square rho G over neta. As it is clear earlier in the theory I have explained, that is R is the radius of the tube, rho is the density of the body falling in the viscous medium, G is acceleration due to gravity, and neta is the coefficient of viscosity. Now all the values are being given to us, so compute the values for R, rho, G and neta, and then we are left with calculations, that is multiplication, division and addition. So after all calculation, the number reduces to 2.72 into 10 to the power minus 4 meters per second.